Now, dear students, chapter number 7 and system of particle and the rotational motion, and we have the topics for the discussion here, that angular momentum and the symbolic notation of the angular momentum is the L vector is there. Relation between the torque and the angular momentum for the system which having the number of the particle. For simplest description, we are just applying the angular momentum for a single particle, and then we will apply the momentum or the angular momentum for the system which having the number of the particle. So definitely the angular momentum is a rotational analog of the linear momentum. Same how we have discussed the one of the quantity earlier, that is called the torque. That is also the rotational analog of the force in the linear motion. Okay. Rotational analog of the force in the rotational motion. So the next quantity we have the L, and simplest way we can assume the define the product of linear momentum and perpendicular distance from the axis of rotation is called angular momentum, that is called the L. So for the convenience, we are just assuming a body in the three dimension which making the rotation about the z axis and lying in the plane xy. So we are just approaching a diagram for a angular momentum for a particle. Now one of the basic diagram which I have shown to you, that the body is lying on a xy plane. As I am just approaching only the change or the angular momentum for a particle that is lying at a point p dash, whose position vector from the O to p dash is the r vector is there. Now as I am just applying the force, so definitely there is a concern of the momentum is also there, that is called the linear momentum, because the particle which is on a which is on a surface, or whatever particle is lying, so whenever the body is making the rotation about the z axis with the omega angular velocity, so this particle will make a horizontal circle in a plane. Okay, so whenever it's make the horizontal circle, so its velocity we are just representing by the tangent, that is called the v. So definitely the mass and the velocity make the concept of the linear momentum. So I have shown the total linear momentum for a particle, and I am just increasing the position vector along the same direction, that is called the position vector. Okay, so the angle between the linear momentum and the position vector, that is called the theta. So just opposite angle, as I am just also approaching, that is called the theta is there. So along the position vector there is another vector, that is the linear momentum. The radial component of the linear momentum is there. Okay, so that's why I have approached the two vectors, two arrows are there. Now what is the perpendicular component, in what direction? The in a perpendicular direction of the linear momentum or the radial momentum, we have the perpendicular momentum is there. Okay, and that is the more important, because always the body is making the rotation in the reference of a perpendicular force or the angular force, or we can say the rotational force is there. Okay, now I am just approaching a vector in a backward direction. Okay, so that's why I am just making a perpendicular on. So this perpendicular having its a value, that is called the r sine theta. Now the simplest formula which I have formed here, L is equal to linear momentum and the perpendicular distance from the axis of rotation. So L can be stated in the term of that L is equal to P into N. So I am just making the simplest relation between them, that P into On is nothing but it is simply the r sine theta. Okay, as I am just making the rotation from the rotation from r to p is there, as the body is making the rotation in the anti-clockwise direction. This is the, suppose this one is the anti-clockwise direction is there. So definitely the angular velocity will be act along the z direction is there. Okay, So as I am just approaching the moment from r to p, so easily we can write the vector notation of the angular momentum, that rp sine theta, as I can write that L is nothing but it's simply the r vector cross p vector. Okay, so this is the simplest vector notation of the angular momentum. Now we have the basic formula that L is equal to R cross P. Okay, so this is the simplest formula we have of the angular momentum. Uh, so this is the equation number one we have. This is the equation number 2 we have. This is the equation number 3 we have, and this is the equation number 4. Now we want to discuss some more things about the angular momentum, about the unit, dimension, its direction, and the components. Now the first point which I want to discuss here, that what is the SI unit of the in the SI system. So I have mentioned that R having the unit that is called the meter, and the momentum having the unit that mass into velocity. So I am just approaching that kilogram meter per second. So finalize, I am just writing it that kilogram meter square upon second. So this is the one of the basic unit we have in the for the angular momentum. Okay, now what about the dimension we have? So what is the possible dimension of the angular momentum we have? So as we know, the mass having the nomination that is m1, and the length having the concern of the l2 and t minus 1, it's the basic dimension we have. Now, some special cases we have on behalf of the formula. As I am just making the theta is equal to 0 between the r and the p. So the L having its own meaning, that is called the 0. The angular momentum is a 0. So here we have to be assume the simply the radial component along with the L. There is a no kind of the meaning of the L is there with the radial component of the linear momentum. Okay, now theta is the 180 degree we have. So although we have the simplest meaning, that is called the L is equal to 0. Now what is the third option we have? So if the theta is equal to 90 degree between the R and the P, so there is a probably L will have the maximum meaning, that is called the RP is there. Okay, so these are the three special cases we have. Now we want to find out the direction of the L is there. What is the possible direction we have? Now to find out the direction of the L, I am just using the two simplest rule. Either I am just using the right handed screw rule or the right hand rule, whatever you are using. So I am using here the right hand rule. So I am just assuming the two vector in the plane. What are the two vectors we have? One of the vector is the R vector, that is called the position vector, and one of the vector we have that is called the P vector. This is the simplest the R vector we have, and this is called the P vector. As we are just making the rotation from R to P, and that is rotation is called the anti-clockwise rotation is there. So probably we are just assuming a right hand inside the plane. Okay, right hand inside the plane, and the rotation of the curling fingers in the direction of anti-clockwise direction. So our thumb will point towards the upward direction. Okay, perpendicular to the plane, directed upward. So it is a possible direction of the angular momentum, that is called the L is there. Okay, so this is the L is there, and that L makes the concept of the R cross P. What is it? It is a vector product. Okay, now same how we are just assuming the L in a downward direction. So what kind of the assumption we should take here? Now we are just making the concept of the R is there in the plane. There are the two vectors. This is the vector R, this is the vector P is there, and we are just making the assumption of that rotation from P to R is there. That is called the clockwise rotation. Clockwise rotation is there. So whenever we are just assuming the clockwise rotation, so the torque will probably will act in a downward direction. Okay, so sorry, not torque, this is the meaning of the L in the downward direction. Okay, the L is the with the concern of that P vector, or either you are just using the negative sign is there, because the vector product is the anti-commutative. So I am just writing that R vector cross P vector. Okay, so I am just using the negative sign is there. Okay, in this manner. Okay, so this is the simplest meaning to find out the direction of the L by the right hand rule. Now the next topic we have the relation between the L and the torque. Okay, so we should keep the relation in our mind that in the linear motion we have the second law of motion, that is called the rate change of the momentum is directly proportional to the applied force. So we want to make the comparison of these terms. So it will be easier method to discuss these terms here or these topics here. So what assume I am there, the angular momentum for a particle of mass m can be stated as that L is equal to r vector cross p vector. Okay, so here we can make the little bit expansion if you want to use that p is nothing but it's simply the meaning of the mv is there. So this is the one of the general equation we have taken. Now I am just making the multiplication of operation divided by dt in the both ends, both side of the equation number 1. Now multiply with divided by dt in both side of equation 1. So we are just approaching that divided by dt of the L is there, that is equal to the divided by dt of that r vector cross mv vector. Now we are just using a identity of the differentiation is there. So what kind of the identity? We are just operating a differentiation in the product. Okay, so from equation number 2, that we are just approaching a divided by dt of that is called the r into mv. How we are just operating? We are just operating, we have the two functions, suppose this one is the u, this one is the v. So one by one we are just keeping and them and making the differentiation of these terms. So I am just starting here. So first I am just making the divided by dt of the r and keeping the mv as it is. Okay, so I am just making that divided by dt of r vector is there into mv as it is we have, plus sign is there. I am just keeping the r as it is and the making the divided by dt of the mv is there. Okay, so this is the simplest representation of the portion of the derivative we have. Okay, now we are just making the little bit changes in this portion. So what I can assume here, divided by dt of the position, so it makes the concept of the velocity is there. So v is there with the concern of the mv is there. So this is the one, in this the bracket we have, plus sign is there, r vector is there. I am just approaching the m is outside and making the relation that divided by dt of the v, and the rate change of velocity is nothing but it's simply the meaning of the acceleration we have. So I am just making further changes. Now here you must one thing notice that if the two vectors those are acting along the same direction, so their cross product is a 0. So v cross with the v, both are along the same direction, so the theta is a 0. So I am just assuming this one as a 0. Now r vector is there and divided by dt of v is the acceleration. So I am just getting that ma is there. Okay, so this is the possible derivative of the right hand side of the equation number 2. So this is the equation number 3 is there. Now use equation number 3 in equation number 2 there. So I have one of the standard equation divided by dt of that L with the concern of that at the place of the divided by dt of r cross mv, I can write the simplest meaning that r cross ma. Ma is nothing but it's simply the meaning of the F is there, that is the force, that is called the force is there. So I am just modifying this one equation. This is the equation number 4. Now I have already told that you must keep one of the equation inside your mind, that second law of motion, the rate change of momentum is directly proportional to the applied force. So I am just making the basic comparison of this term. Now here we have the divided by dt of the p is there. This is the portion in the linear motion we have. Now we have the divided by dt of the p with the concern of that f is there. So this is the basic equation through which I want to make the comparison of the equation number 4. Okay. Now here the rotational analog of the P is the L is there. Here we have the rotational analog of the F is there, that R cross F is the torque is there. Okay. So easily I can make the comparison. So this is the approach we have, the relation between the linear angular momentum and the torque which act on a particle. That d by dt of L is the torque is there. Okay, so it's a analog form of second law of motion. Second law of motion in rotational frame. Okay, so this is the one of the basic required relation we have, and we will discuss so many problems on this concept. Now dear students, we have the next topic, that is torque and the angular momentum for a system of particle where I is equal to 1 to n. Okay, now we can assume, we can consider a system in which number of particles are from I is equal to 1 to n is there. So we can assume total angular momentum L is equal to L1 plus L2 plus dash 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 plus Ln is there, and we are just approaching a vector on it, that is equal to, we are just representing that I is equal to 1 to n and Li is there. So this is the general equation we have assumed. Okay, now angular momentum on the ith particle Li is equal to Ri into Pi. So this is the one of the basic integral we have, and we can make the further changes in it. Li is equal to Ri into, that is called the Mi, and Vi is there. Okay, so this is the simplest general explanation of the term we have. Now we are just saying that equation number 2. Now here we have the torque on the ith particle, that is torque I is equal to Ri into Fi. Now here we can assume the force that is the on the ith particle is there. Okay. Now we will use the sub concept of the linear motion. Force on the ith particle is sum of Fi, that is called the external, plus Fi internal. Okay, and we have assumed the concept of the internal forces for a system in which the number of the particle are interacting, that will be the 0. So the force on an ith particle is only due to the concept of the external force. We are just assuming the force internal as a 0. So here we will use the same concept of the torque is there. So we have the total torque on the ith particle is nothing but it's a simply the sum of the torque on a ith particle, that is called the external torque, plus torque on a ith particle, that is called the internal force. due to the, it is the interaction of the particles due to the interaction. Okay, because we have assumed there are the n number of the particle in a system. So here we have to be use the concept of the linear motion, that as we are just assuming the system having the internal force as the system having the external force is there. So we are just using the same concept is there in the which in which we are just assuming the torque on a ith particle due to the external torque, it is an external torque, and torque on a ith particle, that is called the internal torque. And further we are just assuming the meaning of the internal torque, that is torque on a ith particle is only due to the torque in a ith particle, that is external torque is there. So we will use this one concept is here. Okay, because only the body is making or the system is making the rotation under the action of the external torque is there. So here I am just able to write the meaning of the angular momentum for a system which having the number of the particle 1 to n, dy by dt of L is equal to dy by dt of summation of Li, which contain the I is equal to 1 to n is there, that is equal to I, that is equal to summation I is equal to there Ri into Fi, that is the external force is there. So as we are just making the concept of the external force is there, now for the conservation of conservation of angular momentum for the system, F on a ith particle, that external force is the 0. So we can simply assume this one concept in the equation number 7, dear students. So we are just using the basics of the previous system, that call dy by dt of L is there, that is called the 0, and we easily know that dy by dt of the constant is there. So the system of L1 plus L2 plus dash 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 plus Ln is there. System angular momentum for the system is always remains constant. So this one is a basic assumption which we have discussed, that is based on the previous concept in the laws of motion which we have assumed in the linear frame of reference. So we are just using the same concept for the angular frame of reference also. Now what are the basic components of the angular momentum which we want to discuss here? Now one of the important thing which I want to discuss here, that how can we resolve the angular momentum for a particle which lying in a xyz plane. So I am just taking the angular momentum is an example of the vector product. So I am just writing that L vector is equal to R vector cross P vector is there. R is nothing but it's a simply the x I cap is there, plus y j cap is there, plus z k cap is there. Okay, P is nothing but in the part of the component, that means P x I cap is there, P y is z j cap is there, and the pz along with the k cap is there. So one of the determinant method we can apply same for here, that as we are just getting the components of the angular momentum, that is x component, y component, and the z component of the angular momentum. So we have to be multiply the meaning of that r vector cross p vector. So here we have to be assume the determinant method same as the torque, same for the torque is there. So I am just choosing the I cap, j cap, and the k cap. These are the 3 unit vector, and the component of the r vector is there, x vector, x y, and the z is there. Now next component of the momentum, that linear momentum px, py, and the pz. So how we are just approaching this one matrix? So first which I have told, that whenever you are just starting, so you must keep the separation of the I in the horizontal and the vertical column. So I am just making the separation of the I is there, then after I am just making the components. Okay, so I am just making the keeping the separation of the I. So what I have to do, y is multiplied first with the z is there, then I am just multiplying the z with the py is there. So this is the first portion which we want to discuss here, that first is the I cap is there. So bracket close, First I am making the multiplication of the y with the pz is there, minus sign is there. Now I am just making the multiplication of the z and the linear momentum that is called the py is there. Now I am just starting with the j. As in the determinant, some methodology is there, so we are just applying the simplest method. I am just starting with the j, so I am just approaching the j, minus sign is there in front of the j. Now I have to be choose the components in which the j is not coming in the horizontal line, we are not choosing it, and in the vertical mid column I am just getting the j is there, so I am not choosing the component of the vertical column, those are coming in the j. Now what I have to do here, now for the simplicity I am just making that multiplication of the x with the z and the multiplication of the z with the x. Here one should, you should notice the one thing. Now as we are just getting the component of the angular momentum along the x-axis, so it is it says that the particle lies in a yz plane. Okay, particle lies in a yz plane is there. As I'm just getting the component of the angular momentum along the y direction, so there should be a particle in a xz plane. Okay, so that's why we are just getting the component. Okay, x is a component with the meaning of the pz, minus sign is a z, and the px is there. Okay, now the third component that is called the k cap is there. So I can make easily the elimination of the z in a horizontal and the vertical line. Those component I will not take. Okay, now we are just getting the component of the angular momentum along the z axis. Okay, so if the momentum is acting along the z axis, so you must pay the attention in which plane the body will lie. So it will lie definitely in the xy plane. So I am just getting the two component, x with the py and the y with the px. Okay, so these are the basic components we have. Now x with the py minus y of px is there. Okay, so this is the third portion we have. Okay, so these are the basic components of the angular momentum, and on behalf of that we can solve the one of the numerical. Now dear students, we have the NCERT question number 7.6, and the statement of the question is there: find the component of the L along the XYZ axis if a particle move along the XY plane, the L having only the Z component. So already we have done this one work. As we know, the L is the vector product. Okay, so of the R and the P is there, so we have mentioned the R and the P components in the term of the component, and we have gone with the solution with the determinant method. So I have made the different component. Now this component is along the this component. Okay, so these are the components we have. Now this is the component of the angular momentum along the x-axis we have. Okay, this is the component of the angular momentum along the y-axis we have, and this is the component of the angular momentum about the z-axis we have. So whenever we are just getting the opportunity that a particle is moving along the xy plane, so definite it having the component along about the z-axis. Okay, so the momentum is acting along the z-axis having the component that is called the xpy minus ypx is there. So you must understand the basic statics of the angular momentum, or the component concept of the vector product is there. If the particle is lying in a xy plane, the x is a reference of a position vector is there. Okay, along the x-axis, this is the part of a position vector we have. And definitely this is the momentum along y-axis. So definitely it gives the concept of the L along the z-axis is there. Okay, so this is the simplest meaning we have. Either these are the vector quantity, so you can apply the vector is there. Okay, so this is the simplest meaning of the question we have. So this is the all about the angular momentum, formula of the angular momentum for a particle Now the relation between the torque and the angular momentum, as already we have discussed the concept of the second law of motion in the linear motion, F is equal to dy by dt. So we have the simplest meaning that torque is equal to dy by dt of the L is there. And how can we discuss the angular momentum and the torque for the system which having the number of the particle 1 to n is there, and we can apply the simply the concept of the external torque is there on the system for the conservation of angular momentum should be the zero. Okay, always the system is making the rotation and the influence of external force is there. And how can we discuss the component of the angular momentum in the particular directions? Okay, so along with the question number 7.6. Okay, thank you.